Good morning, my name is Steve Cuppy, Indiana Microelectronics, and I'm here today to talk about reconfigurable microwave filters to mitigate co-site interference and jamming mitigation. Indiana Microelectronics, our research and development on reconfigurable microwave filters, sometimes called tunable microwave filters, to date has been largely sponsored by two SBIR projects, one sponsored by DARPA and the other one by the United States Navy. It is an STTR project. It's a cousin to the SBIR program. If you're not familiar with that, feel free to contact me after the presentation. So let's set the example. Let's set the scenario in terms of what we're trying to accomplish at Indiana Microelectronics. Suppose a soldier is out in the battlefield and the communication system that the soldier is operating is not functioning properly. And it's not functioning properly because of interference that's being received from other transmitters in the area. There's two cases of what could happen is that one, the interference could be another system operating legitimately that happens to be either too close or too powerful or a combination thereof that is actually operating legally or appropriately, but still interfering with the system that that particular soldier is trying to operate. Another scenario is when the adversary is trying to intentionally jam your particular system and degrade the performance and deny the soldier the use of that particular situation, of that particular communication system. So there's a lot of things that can be done, and the Air Force, the Navy, and the Army are all throwing all the different technology approaches at solving the co-site interference and jamming problem and trying to solve that issue. And you can approach it from a multitude of different angles. One is simply you change radio frequencies. Sometimes that's not the option, or you still have the same effect. That's a simple one, but essentially in terms of equipment design, there's three approaches that are being used. One is antenna-based, the other one is RF filtering-based, and the third one is digital signal processing-based. The solution at Indiana Microelectronics is the analog RF filtering section. And as I said again before, the Army, the Navy, and the Air Force is approaching this and throwing all the solutions at the problem, because it is, as one very senior RF design engineer told me, that had more than 50 years experience. RF interference is here today, it's getting worse by the hour, and it's only going to get worse in the future. So what's our solution? Our solution is a reconfigurable microwave filter. And I'm going to describe in the following slides in terms of what we do, how we do it, and give you the base architecture in terms of how we approach our design of our reconfigurable microwave filters. The ultimate benefit is that you have access to the battle space, which means that the system that the soldier is working on operates the way it was intended to, even though it's in the midst of interference that's either coming from friendly systems or it's actually coming from the adversary. And the advantage of our filters is that they're dynamically reprogrammable, which means that in one area 1 minute you may be able to have certain frequencies that are causing interferences, and those frequencies may change in a matter of minutes. Our filters, you're able to dynamically adapt, dynamically program what those frequencies and what frequencies either you notch in or notch out are. So let's set up from a spectrum perspective. Let me set up the situation here. Along the x-axis is increasing radio frequency. On the y-axis is increasing power at various radio frequencies. So for those that are familiar with it, sort of like a spectrum analyzer, a plot on a spectrum analyzer. The blue diamonds in this example are the signals of interest. Those are the signals that you want to get through and look at and to be able to process with whatever system that our filter is connected to. It could be a radar system, it could be a SATCOM terminal, it could be a ground-to-ground or ground-to-air or air-to-ground communication system. The black spikes you see there that are labeled interfering signal, those are the signals that are causing you problems, that are denying the soldier the use of that particular communication system. The reason this is important is that what our filters do is it gets rid of in-band, out-of-channel interference. Sometimes those black spikes are so large that they swamp the front end of whatever receiver that you have. They could swamp the front end from the perspective of putting the low noise amplifier into saturation, or it's actually denying the digital signal processors the full dynamic range of the analog to digital conversions. And that's a very important point, very subtle point, but it's an extremely important point, is that essentially what our system does is it allows the farther end system, and most things are digital these days, it allows the radio system, the receiver end, to use the full range of its analog to digital converter. And the advantage of why Indiana Microelectronics and why hasn't this done before is that we concentrate in 1 gigahertz and above. A lot of communication systems are moving higher in frequency, and that seems to be a trend. And the effectiveness of traditional transistors, resistors, capacitors built on traditional printed circuit boards is you can't, as you get higher up in frequency, those approaches that are able to be done at 100 megahertz or 200 megahertz or 300 megahertz are no longer effective. They just don't have what's called the quality factor in order to provide the necessary attenuation or the bandpass filtering requirements. This is an example of a notch filter solution. Our filters can be fabricated in either bandpass configurations or notch configurations or a combination of the two. But in this particular one, we're going to look at a notch filtering solution using the previously set up example where the blue diamonds are the signals of interest and the black spikes are the interfering signals, whether intentional or unintentional, is that in this case we have a 4-pole notch filter. And you can see where it has dips down where on each of the spikes where you see a dotted line. That's an actual notch where we're attenuating the frequency or attenuating the signal at that particular frequency. This is a case of a 4-pole filter where we have independent control over each of the 4 poles. And the advantage of that is that if you have 4 interfering signals, you can attenuate 4 different signals. If you have one large interfering signal, such as the one on the right, the black spike on the right, you can park 2 of the poles on that larger interfering and allocate the other 2 poles to 2 separate interfering signals as shown on the 2 on the left-hand side. So really it provides a lot of flexibility. Not only do we have independent tunability over each of the 4 poles, is that each of the 4 poles can be dynamically changed. So for example, we've been able to show that we can tune a filter, have octave tuning that's over a factor of 2 bandwidth, tune from say 1 gigahertz to 2 gigahertz, and tune each of the 4 poles over the entire bandwidth and notch out whatever particular interfering signal that may be there. This is a result after the attenuation of the signals. You can see where the interfering signals, the black spikes, have largely been diminished, as well as, and that will allow go into the up front or the down end processing system. So that would hit the front end of the particular communication system that you're seeing. So you can see if you had that great big large spike and that was in the band that's being digitized, you'd be using a significant portion of your analog to digital converter in order to digitize nothing more than interference. With our system is that you can notch out some of those interferers, bring it down such that the largest signal in the entire spectrum that's being digitized is the signal of interest, which will make the entire system work better for whatever that particular communication system is designed to achieve. The baseline technologies used today, believe it or not, one of the baseline technologies is live with the interference. I mentioned other techniques that we talked about in terms of antenna techniques that are used, antenna steering, beam steering sometimes it's called, as well as in the digital signal processing world, being able to take an interfering signal that's right on top of your signal of interest. And it's really amazing what the DSP people can do in terms of pulling the signal out of noise when the interfering signal is right on top of it. But as a number of those companies have also told me, he says, unless I have a good signal coming in, I can't use, my digital signal processing won't work very effectively. So it's, as I said before, you have to have the antenna solution, you have to have the analog RF solution, which is what we concentrate on, as well as the digital signal processing solution. Another technique that's commonly used is static filters. You know where the interference is, the interference doesn't move, it doesn't change, you buy a filter, you put it there. The problem is that rarely is static interference stay in the same location for a long period of time. It's going to be changing, especially if you're in an environment where you have an adversary that's intentionally jamming you. That signal's going to be changing and trying to mess you up. Another one is YIG filters. They're very expensive, heavy, and require a lot of power. Main requirements that we're seeing from customers are what's called high Q filters, Q meaning quality. There's a technical definition about that, but can you get a lot of attenuation over a very narrow bandwidth? When you get a lot of attenuation, a very narrow bandwidth, that's called a high Q filter. So we want low insertion loss. We don't want to everybody has a power budget, especially on the receive side, and everybody's very sensitive to giving up any of that power that goes into the front end system. So you have to have very low insertion loss. Typically our insertion loss is less than 1 dB for the passband. Also, you want very sharp filter walls because you may be trying to get a signal of interest that's right adjacent to the interfering signal. Also, as I said before, the key thing of our filters is tunable filters, manually tuned via a graphical user interface where the soldier could actually plug in through some other system that they know where the interferer is and they manually plug it in, or it's automatically tuned via some sort of software control, which could be either on the filter itself or being connected to whatever system to which it is embedded. Here's the basic sauce of how we do our manufacture our reconfigurable filters. For most RF engineers, you're very familiar with cavities, cavity resonators that are milled into blocks of metal. Instead of milling them into blocks of metal, we're manufacturing our circuits, our cavities, actually coaxial cavities inside printed circuit board material that can be made by a number of manufacturers. These are called, and you can see there's a bandpass filter that has 3 resonators, and they're cascaded together, and commonly these in the literature are called evanescent mode cavity filters. On top of the filter, on top of the cavity resonators, we have capacitance control techniques. The cavity itself is the inductor, then you put a capacitance control on top of it and be able to control that, and there's 3 different types of capacitance control, varactors, piezoelectrics, and RF MEMS. Each one has its own advantages and disadvantages. If you're interested in that, you can feel free to talk to me afterwards. We're finding it's quite useful or very effective to use varactors, which are cheap, easy to control up through the C band, possibly into the X band. C band is 4 to 8 gigahertz, X band is 8 to 12 gigahertz. Here's an example of some of the work that we've done. The upper right-hand corner is a piezoelectric based filter. The bottom right-hand side is some of the control hardware, control and feedback and control hardware that we built in order to control the filters. For varactor based, you don't need feedback and control. It's basically a table lookup. If you're going to use piezoelectric or MEMS to adjust the capacitance, you need the feedback and control, which is a science in its own right and something that we're continually working on. Performance specifications. Our filters have Qs up to 700. We think that's quite impressive, especially sometimes the Qs that people have on the open market are less than 100. Tuning range, typically we get a 2-to-1 tuning range, which means that if it's in an L band, we tune from 1 to 2 gigahertz. If it's in the S band, it's 2 to 4 gigahertz. If it's in the C band, it's 4 to 8 gigahertz. Tuning speeds, we've demonstrated down to 5 microseconds tuning speeds. We're working on that. We think we can get down to 500 nanoseconds or less in terms of tuning speeds. And we can get very small bandwidth percentages. For a notch filter, we can get less than 2% bandwidths for our filters. And as I said before, one of the special attributes which is really nice, is that each pole is independently controllable. So instead of having the filter all on one frequency, attenuating one frequency. You can attenuate multiple frequencies at the same time. That adds a lot of flexibility. It's like you're getting 4 filters in one. Features, advantages, and benefits. We've talked about pretty much a number of the different features today in terms of independent control over the filters. It can be fabricated in standard printed circuit board materials. It's largely based on, COTS technology. And the real benefit is that it provides the soldier with access to the communication system and to have that communication work as designed without being denied access to that particular communication system, whether it be a vehicle-mounted radio, a handheld radio, or a SATCOM terminal. Current state of development is that our varactor-based filters are in TRL level 6. We think we're going to be able to get that up to TRL level 7, technology readiness level. For those that may not be familiar with it, TRL 7 in the next month or so through some testing that's being done by the United States Navy. And we're continuing on through our not only our Phase 2, our STTR Phase 2, but the Navy recently exercised the Phase 2 Option 2 contract to continue the development of these filters. Indiana Microelectronics is located in West Lafayette, Indiana, near Purdue University, and we're currently in 5 employees, including my business partner, Mike McFeeters, back here in the blue jacket. So either grab one of him or me afterwards if you're interested. And my name is Steve Cuppy, Indiana Microelectronics, located in West Lafayette, Indiana. If you have any questions, I'll be glad to answer.
Steve, I'm going to take the first question. How do you envision the employment? Would this be a separate device that I would plug into my existing radios and vehicles, or would this be embedded in the existing equipment?
Both. It could be both.
Okay.
In the long run, it's best if it's embedded into the equipment from the design phase. But if there's co-site interference or jamming mitigation of a particular piece of hardware that's having problems, we could implement this as a standalone upfront, plug it in between the antenna and the communication system.
Right. So the biggest challenge is, from an Army perspective, as the last 5 years we've reinvested into many of our new devices, is how long is it going to take to say, okay, we now know we can do this, and do you get the requirements guys to say, yes, we can do this, and now we want to do this? What does it take to refit all the existing equipment?
Depends upon the program.
Right. Okay. All right.
Wish I do.
Any more questions? Thank you, sir.